Okay, so hi guys, welcome back to my channel. So from today onwards, I'm going to start a new playlist which is Kafka. Okay, so in this playlist, I'll be recording each and everything about Kafka and will reach from 0 to 1 in Kafka. This playlist isn't about just theory or it's not restricted to just theory. We'll see the installation, we'll see the messages handling, and we'll see the architecture. So starting from the theory, each and everything or advanced Kafka, or will be uploading videos in this playlist. Okay, so just stay tuned. So let's start some theory and the basic understanding of what Kafka actually it is. So every company runs on data. Okay, runs on logs, runs on metrics, transactions, and the real problem was never generating the data. Okay, it's about moving the data from one system to another. Okay, and handling the massive amount of data from one system to another. Okay, so it's about moving the data from where it's created to where it's needed. Okay, so Kafka isn't a database, or it just isn't a simple queue. It's a system built to move and store continuous streams of data at scale. Means handling large amount of data or sending the large amount of data from one system to another with keeping scaling in mind. So let's start with publish subscribe messaging. So I'll be slowly throwing some of the jargons because I want you all to be comfortable with all these words that we'll be using in our later videos. Okay, so what is publish subscribe messaging? Okay, so a publisher doesn't send a message to one consumer. Now your question will be, what is publisher? Okay, so publisher is the one who will publish the message. Okay, and the publisher doesn't send a message to just one receiver. Okay, it just labels the message. Okay, it just labels the message, and any number of subscriber can register interest in that label. Okay, now what is the subscriber? Subscriber is nothing but the consumer which will subscribe to that label, that I am interested, I'll consume the data. Now a broker sits in the middle to make this possible. Here I have simple diagram in order to explain this Kafka. Now what is broker? Before moving to the diagram, let's understand what is broker. So broker is nothing but a Kafka server that contains partitions, topics partitions. So a broker sits in the middle to make this possible. The whole point is decoupling. The publisher never needs to know who's listening and how many listeners exist. Just simple, you'll see this is the broker, this is the middleman, or we can say this is the Kafka server which contains the partitions. This is the publisher who will put the message. Publisher who will put the message. Again a publisher who will put the message to broker. The subscriber who will consume the message. Subscriber who will consume the message. Again a subscriber who will consume the message. So this is the basics of what Kafka is. So now let's see how it starts. There is the direct connection, point to point mesh, and with the pub sub with a broker. First let's see what is the problem that we face in order to use the direct connection. So if you can see, there are 3 producers and there are 3 consumers. If you are using a direct connection, then you need to have 1, 2, 3 connection, again 1, 2, 3 connection, again 1, 2, 3 connection, and this has become a mess. So you need to have n cross m connections. But as soon as you introduce this broker, your n cross m consumers will come down to n plus m connections. Okay, sorry, I'm talking about the connections. So route everything through one broker and you all need only n plus m connections. So now this math is the entire justification of why broker is being used. What is the use of broker? But the actual definition is broker is nothing but a Kafka server that contains the partitions. Okay, just remember this. Now we'll enter Kafka. So Kafka is described as a distributed commit log, or more recently a distributed streaming platform. Before understanding the Kafka, let us understand what is commit log. So if you see the database write ahead log, which is durable, ordered and replayable, means durable means it is on disk, ordered means strict sequence, and replayable means we can rebuild state from scratch by reading it from start to end. Okay, what does it means? So every entry written to the log is physically saved to the disk, not just kept in memory. This means even if the process crashes in between, the machine reboots and the data survived. How? Let's get deep dive into this. So as we have discussed about this data write ahead log, so what it does, so imagine if you're hitting a update query or insert query. So what do you see? Okay, so you hit an update query and insert query and the result is in front of you. But is it actually happening that the update query and insert query is directly hitting the database without performing any of the single operation? No. Why? Because when you run an update or insert database like MySQL in Postgres, we assume that database directly changes the data file. but it doesn't. Why? Changing a data file is slow, multi-step disk operation, and if the machine crashes halfway through, you get a corrupted file data. Means the database operation is not a very lightweight operation or not a very straightforward operation. So before performing any operation to the database, you need to store it somewhere, so that if in the middle of the part there's something happens, then you can replay it. Okay, so that's the whole point of database write ahead log. So this is the simple biggest mental shift from a traditional queue like a RabbitMQ. What RabbitMQ is? So RabbitMQ is a normal queue. A consumed message is typically gone. In Kafka, consuming a message never deletes it, it just sits in the logs. Here is the analogy to compare what RabbitMQ and Kafka is. You can take an example of RabbitMQ as a postman. Postman delivers the message and the message is gone. And you can understand the Kafka by assuming that it is a newspaper stand. Every newspaper will be stored here. You can read it anywhere, anytime, and a week later. So that is the difference between RabbitMQ and Kafka. Okay, and this is what database write ahead log is. I hope you understood. Now let's understand a little bit about this messages and batches, what it is. So I'm slowly clearing each and every jargon so that it will be easy for you to understand. I might be repeating each and every keywords again and again, so don't worry, just bear with me till the end, and I'll make sure that you'll become expert in Kafka. So first one is the message. Message is an atomic unit of data, okay, just an array of bytes to Kafka. So what is key? It is then optional bytes attached to a message. So every message will contains a key which is used to decide which partition it lands in. Now what it is, okay, so when I was explaining the concept of broker, I have told that broker is nothing but a Kafka server that contains different partitions. Okay, so let's say this is the broker which contains partition 0, partition 1. Now message came, but it lands to which partition? Partition 0 or partition 1? Who or what is the deciding factor? This formula is the deciding factor. So let's say you have 10 modulo number of partition, which is nothing but 5. So whatever the result we will get, the message will land into that partition. Okay, so is there any possibility, tell me one thing, is there any possibility that the result that what we get will be greater than this or will be equal to this? No. So if we are mentioning number of partition, then we guarantee that if we are mentioning number of partition as 5, then the messages will land in 0, 1, 2, 3 and 4. That's the power of this formula. Okay, if you ever change the partition count on a topic, this mapping shifts and messages with the same key are no longer guaranteed. Okay, so let's say at first go you have decided that this is the key and this is the partition logic, but now in the middle of nowhere you came and you'll say that okay, the formula to calculate the partition is changed. Now this mapping is shifts and the messages with the same key are no longer guaranteed to land where earlier the same key messages landed. Each and everything I'll cover in very detail, just bear with me. That's the real production landmine. Now let's move forward. What is batch? Okay, if you are in a computer science team, which I assume that you are, so you have heard this term batch many times. It is nothing but a group of messages headed to the same topic. We are sending a group of messages to the same topic through batch processing. This is it. Now we are actually moving to the main thing, which is nothing but the schema, the more confusing part. I'll be breaking this part into chunks. I'll be taking multiple use cases. So just listen this part very carefully. Okay, schema. So imagine your producer app send this message to Kafka. User ID 42. Action click. Timestamp this. Now for Kafka, this is a raw byte. Okay, it has zero understanding that this is JSON. Okay, Kafka don't understand this. For Kafka, everything is byte. Be it the photo, be it the characters, be it a random string or anything. Okay, so for Kafka, everything is bytes. Now what is the problem? So the problem shows up in the consumer side. Okay, consumer side need to actually read user ID action out of that message to do something useful. Means for Kafka, this is in bytes, but whenever the consumer will consume this message, they need to understand in which format the data is coming so that they can actually do the useful. So for that to work, the consumer need to know the exact structure in advance, the field name, the field type, field order. That agreed upon structure is the schema. So the mutual understanding between the consumer and the producer that okay, Producer will say that I'll be sending the format, I'll be sending the data in this format. Consumer will agree, okay, I'll be receiving the data in this format. So that agreed upon structure is the schema. So now let's understand why JSON is risky for long term. So after few months, if someone on the producer team decides to rename action to event type, or changes the timestamp from number to string, so every consumer reading that topic will silently break and misread data, and nobody gets warned. Okay, let us understand with an example. So day one, everything is working fine. You send user ID, you send action, which is click, you send the timestamp, which is this. Okay, now the consumer uses this library, which is nothing but the JSON, to pass the data. This is in the JSON format, and this is the very famous library, which is JSON library, which will be utilizing this object mapper in order to pass the data. So JSON node will pass the data, read tree message, and from this node we'll be hard coding the action. We want to utilize this action, so we have hard coded this action, and we are actually extracting the text. So we got event type. Now we will be processing the event type. Now. After 6 months, producer team rename the file from action to event type. Now what will happen? JSON node is equals to mapper.read tree. This string event type is equals to node.get action is this. This actually throw a null pointer exception. Why? Since the field is no longer exists. Since the field is changed from action to event type, this will silently break. Okay. Now you will say that why to use or why to hardcode this value when we have another library to use. So using Jackson's POJO mapping approach, which is very famous approach these days in the production. So what we'll do, we'll make a class. Okay, we'll make a class and we'll assign some fields into it. Okay, all the fields will be assigned, and we'll be using the mapper.read value to convert the message, which is nothing but JSON, to click event.class. So every field in this message, which is nothing but user ID, event type, timestamp will be converted based on the click event class. Now what will happen? Even if the name is changed from action to event type, there will nothing be happen. Why? Because inside the mapper used the reflection to map the message to the classes fields. So what will happen? The version is extremely common in production Java services. This is exactly the silent breaker scenario. Event.action is simply null. The pipeline will start counting as unknown or null value. Whenever it will get the mismatch between the message and click event class, it will ignore. It will treat as an unknown or null value. Okay, it doesn't care, but it will not break as this one. The code will not break as in this case. So now if this is the problem, but at some point of time this solves our problem. Why? Because the code will not break. The code rather will be treating it as unknown or null. Then what is the problem? So now what is the solution then? So let's move. So instead of writing out user ID, action, timestamp, which we'll be doing till now, as every message we'll be sending or posting to the broker, every message will contains the user ID, contains the action keyword, contains the timestamp, every message. Now Avro stores the schema ones separately in schema registry. The actual message just contains these raw values referencing that schema by ID. Let me explain you properly. Now what is happening till now, in every message we are sending the keys like user ID, action, timestamp. The whole point of evicting this is what we'll do, we'll store these things inside the schema, and every time we'll be utilizing the schema, we'll not use this keyword in order to send the message. We'll use only these values to send the messages. So what we'll do, by using this approach, messages are much smaller, no repeated field names for every message. Okay, the next useful thing is Kafka can enforce if someone tries to publish a message that breaks the agreed schema. Let's say producer has agreed on one schema, consumer has agreed on this schema. Now something broken will be caught at the runtime, okay, at that moment of time. Okay, so it's not like that in the production some point of time we'll check that okay, data is wrong or some mapping is wrong. Then even if it is not a failure, but still it is a failure. Why? Because we are considering it as unknown. The data, the important data never reached to the consumer. Okay, or it will be reached, but the consumer side will treat unknown or null. Okay, so I hope this is clear. Let us understand the Avro version. So this is the way we'll define the schema. Okay, in the schema, type is record. Okay, first type is user ID, type is int. Second is action, type is string. Third is timestamp, type is long. So the schema, the definition of what fields exist and their type gets written down once and stored centrally. In the schema registry, this will be stored once and will be utilizing every time whenever the producer post the message to the broker or to the partition. So every time what the message looks like, we'll be sending the schema ID. We'll be sending the values of user ID, which is nothing but 42. We'll be sending the value of action, which is nothing but click. We'll be sending the value of timestamp, which is nothing but 169, blah, blah, blah. So every actual message sent to Kafka contains this. No overhead of sending each message like user ID, value 42, action, click, timestamp, this. Why to send every time this key? So Avro solves our problem this way. Now let's see. So this is the producer. It fetches the schema ID 7. This is the Kafka message ID and the value. The producer registers the schema with the registry just once. Now getting back an ID 7. For our example, let's say the ID is 7. So every message it produces is tiny. Every message the producer produces is very tiny. Just ID 7 plus raw binary values. No field names repeated anywhere. Okay. Now the consumer fetches the actual schema. Consumer fetches the actual schema based on this ID from the registry and uses it correctly decode the binary bytes. The arrow is here, the arrow is here, the arrow is here, the arrow is here. I hope you understood. Now let us see some of the difference between the JSON XML and Avro registry. So breaking changes. It ships immediately, no resistance. It will not break anything at runtime or at the point when producer will produce the message. You can compare this thing like Java and Python. Okay. At Python might sometimes compile the broken code, or if it is having the compilation error, then also it will compile it. But Java at the time of compilation, it will stop you. It will not let you compile the code until unless you will fix the compilation issue. So Avro is just like Java, blocked at exact moment it's attempted. Why? Because if you see here, if you add some other fields, they will say that okay, we agreed on these 3 fields. Why? Another field. The type of this field is, okay, let's say action is changed to something. So the ID is present to the producer, ID is present to the consumer. If you'll change the action name, both will have the same agreement. Okay, I hope this is clear. So when they find out, okay, or before that, who finds out? Nobody, no error anywhere. The developer right there in their own terminal will find the issue, or will find that the data they are sending is corrupted, or the data they are sending is not what they agreed upon. Now what they find out is weeks later, maybe if someone notices bad data, okay, instantly before the code even reaches to the production. What breaks? Every consumer downstream will break silently one by one. Nothing. The bad message never leaves the producer. Producer is trying to put the bad message, they will be receiving the error at the compile time only. Now the painful investigation across servers and logs you need to see. You already know the stat trace is pointing at the same schema conflict that you are pushing the bad data. You can understand with this small example that JSON path, file renamed, ships to production, founds a week later. File renamed, registry checks it, blocked immediately. Okay, I hope this is clear. I hope you got the difference between the JSON and this Avro. Okay, so now let's move to this topics and partitions. Okay, so this is the very important part, and just listen it very carefully. Why? Because here is the most confusing part, which more developers gets confused when they study about topics and partitions, or they will just read the definition and they'll just cram it. Okay, they'll not understand what are the different use cases that we can have. Okay, so let's understand these topics and partitions. So think of a topic as a folder name. Example, user click. Every message about user clicks goes into this one folder. Let's say you have user click 0, you have user click 1, you have user click 2, you have user click 3, each independently ordered. Now why to split up this user click into 4? So by splitting into 4 partitions, you can spread the work across 4 different servers. 4 partitions means 4 different servers, 4 brokers, and have 4 consumers reading in parallel instead of 1. So we can have consumer 1, we can have consumer 2, we can have consumer 3, we can have consumer 4. So instead of reading all the consumers from broker 1, we have split it to broker 2, we have split it to broker 3, we have split it to broker 4. So any request can goes to any of the broker. This is called scalability. Now what is the ordering rule? So when user clicks 3 buttons in a row, click A, click B, click C, if those 3 messages happen to land at different partitions, so let's say this producer who is pushing the message click A, click B, click C, we have partition 0, we have partition 1, we have partition 2. So click A, land to partition 1, click B, land to partition 0, 1, and click C, land to partition 2. Now what will happen? Which can happen randomly if you don't set a key. If inside the message I'll not set the key, they can randomly go to any of the partition. Now you will say, what is the difficulty, what is the problem which we will be facing if randomly some messages will land to some random partitions. Now a consumer could see click C before click A. Total chaos for anything that needs sequence. You have clicked one folder, okay, then this folder will open. Now if you will not set the key, if the ordering is not guaranteed, you must see this click first, then this click, then this click, exact opposite, or any random order. So this is where ordering rule is important. Now the solution is, when producing, you attach a key, in this case user ID. So Kafka guarantees same keys always goes to the same partition. So for the 42, let us say for our example the key is 42. So every click for that user will land to partition 0 for our use case. So that in partition 0 we'll get click A, click B, click C. The order is guaranteed. I hope this is clear. Ordering rule. Now let's move forward. The order is strictly guaranteed. Meanwhile, user 99's event might land on partition 0. Also strictly order among themselves, just one different on a different log. Now the ordering inside each and every partition 0 P1 is guaranteed. What not guaranteed is what we are going to see now. This is the most important use case. Okay, so across the whole topic, if the user 42 clicks land on partition 2, user 99 click land on partition 0, there is no promise about which one consumer see first. Relative to each other, this is very important, relative to each other, because we have guaranteed that inside that partition 0, inside that partition 1, the ordering is guaranteed, but relative to each other, which message will occur first is not guaranteed. I'll explain you with a very best example. Okay, because there are two completely separate logs being read potentially at different speeds. Okay, that is why the ordering relative to each other is not guaranteed. Okay, now two users are clicking almost at the same time. Let's say 42 clicks A, which reaches on partition 2, 99 clicks X, partition 0, 42 clicks B, partition 2, 99 clicks Y, partition 0. Now the partition 2 will looks like A and B. Why? A, B. Partition 0 will look like X and Y, X, Y. Now what will happen? Inside each partition the order is guaranteed, A, B, X, Y. So within partition 2, you will always read A before B. Within partition 0, you will always read X before Y. Now the consumer sees in this order X, A, Y, B. Why this? Why even we considered this use case? Okay, why this happens? Okay, you can see still the order is maintained. X is before Y, A is before B. Still the order is maintained, means A has to come before B, it has came. X has to come before Y, it has came. But relative to each other, which message will occur first is not what Kafka guaranteed to us. Okay, a single consumer reading the whole topic is really pulling the two separate logs independently. Means a consumer is reading the whole topic, is really pulling all the messages independently, and that's where this use case occurs. Okay, the only timing guarantee, again the Kafka is saying, the only timing guarantee you can lean on is within the same partition, means partition 0 and partition 1. Within the same partition the ordering is guaranteed. Anything across partition is a coincidence of network, broken timing, not a promise which is actually done by Kafka. I hope this is clear. Now why cross partition ordering is a problem, why it is even a problem, or why we bother about it. Okay, so let's say a single Kafka consumer instance in the code isn't logged to reading from just one partition. Means a Kafka consumer is not restricted to read the value from one partition. They can read from any partitions. Okay, let's say for this example, a topic is subscribed, Kafka assigns the partitions to own. Okay, now this consumer is reading from partition to partition 0. Now the producer the producer each key message by user ID. Let's say key 99 hashes to P0, key 99 hashes to P0, which lives in broker A, key 42 to P1, key 42 to I guess P1, partition 1, no, I think it will be partition 2, which lives in broker C. Now these routing decision happens once at production time. Okay, you'll think that whenever the consumer needs to read, every time they will check that okay which partition to look up at. No, at only once this will happen at production time and never changes for that key. Each broker holds its strictly ordered logs. Each broker will hold its strictly ordered logs. Now consumer sends fetch request to both brokers. Consumers send the fetch request to both the brokers, and whichever will reply first is what gets processed first. That's the mechanical reason cross-partition order isn't guaranteed, even though each individual partition's internal order is maintained. Means they have requested broker C, they have requested broker A. Whichever broker is more active, they'll send the data. Inside the partition, the order is maintained. Inside this partition, order is maintained. Relative to each other, the order is not guaranteed, is what actually Kafka is saying. So let's see the everyday version. No Kafka. Imagine you have two WhatsApp chat. Okay, open. One with friend 1 and the other with friend 2. Both friends are typing message to you. Now friend 1 has typed hi and then how are you. Friend 2 has typed hey what's up. Means friend 1 has hi how are you. Friend 2 has hey what's up. Now inside each and every friend's chat, the ordering is guaranteed. Till here it is clear. Within friends 1 chat, we'll see hi before how are you. WhatsApp guarantees that obviously. Okay. But which chat pops up on your phone first at the given moment has nothing to do with who typed first. It depends on things like whose phone has better signal right now. Did you understand where this X, A, Y, B came? Okay. Even if X is coming before Y, A is coming before B, but it is possible that X, A, Y, B can happen just like here. So my phone notification feed might get slow. Okay, first I'll get hey, then I'll get hi, then I'll get WhatsApp, then I'll get how are you. The same example as X, A, Y, B. Okay, friends, two messages are in right order. Friends, once two messages are in right order, but if we map exactly to Kafka, friends 1 chat means partition 0, all of users 92 events. Friend 2 chats, partition 2, all of user 42 events. And Kafka is also guaranteeing, again I'm saying, partitions, individual partitions guarantee the strictly ordered messages. Okay, but relative to each other, just like the notification feed, the ordering is not guaranteed relative to each other. Okay, I hope this is clear. So that's it. That's the entire mechanism of X, A, Y and B. So isn't Kafka doing anything strange? Okay, is the Kafka doing anything strange? Exactly the WhatsApp notification feed situation, just like brokers. So Kafka is not doing anything strange. It is actually following the rules which needs to be followed. Okay. Now, why should we actually care this use case? Where this use case will break our entire business logic. Okay, 99% of the time we generally shouldn't care. User 92 and 42 don't need to be proceed in right order relative to each other. Relative to each other, they don't care. They will only see XY, they'll only see AB. They'll not see relative use cases. Okay, but the 1%. So building a flash sale system, only one item left in the stock. Let's say there is only one item which is there in the stock. Whosoever buys event gets processed first, wins it. The user 99 clicks at 10:001:000. User 42 clicks 10:001 and just 50 milliseconds later to 99. So exactly this is very clear that user 99 click wins and the user 99 should get the product. Now what will happen? Let's say 99 event lands on broker X, partition 0. 42 events land on broker Y, partition 2. Now the consumer, the same situation, if you'll see the same situation here. So if you'll see this broker that's momentarily a bit slow, broker that responds quickly. Now the consumer might process 42's buy first. purely due to network timing. It sends the request, it has given the request response faster rather than this. So 42's event will get to the consumer, okay, and the system wrongly gives the item to 42. Instead of giving the result to 99, which is the clear win, the consumer or the system has given the result to 42. That's the why bothers. It only matters if your business logic secretly depends on who did first across different user entities, okay. This is just a business logic, okay, that we have implemented. So we have decided one architecture and we are following one business logic, okay. So if you do not have cross entity race conditions, this ordering quirk is completely harmless, okay. If you do not have the relative ordering across each partitions, this case is entirely like depreciated for you, okay. Now what is the solution? If this is our use case, what is the solution? So the solution is to change the architecture. Now what is the solution? Let us discuss one by one. So the first solution is key by the contested resource, not by the actor. What does this mean? Remember, when we were designing, we have selected user ID as the partition key, which is nothing but 42. So instead of choosing the user ID, let's say what happens is, so we have selected the user ID as 42. We have selected the user ID is equals to 99. So there are two brokers, broker 1, or we'll say there are two partition 0, partition 1. So let's say the 42 event will land on partition 0, 99 event will land on partition 1. Now what will happen? The item, this item code which is 1, okay. So inside the partition 0, partition 1, there is a chance that even though the partition 1 wins, there is a chance that partition 0 will send the response faster. So instead of using the wrong key, which is the user ID, because Kafka guarantees that for the specific keys, all the events will land to a specific partition. Then why to keep the user ID as the key? Why not to keep the item ID as the key? Okay, so wrong key is user ID. User 99 bits and user 42 bits can land on different partitions, as you can see, different partitions. Now fixed key is item ID. So if we have fixed the key item ID, so there is guarantee that this item ID's response will land to partition 3 every time this item ID responds. So no matter who has clicked it, user 42 has clicked it, item ID will go to partition 3. 99 has clicked, item ID 1 go to partition 3. Now user 42 bit will land on same partition, user 99 bit will land on same partition, and the Kafka guarantees that inside the same partition we guarantees the strict ordering. So both bits are now racing to hit the same broker and same partition. Whichever one generally gets the first is written to offset 0 and the other to offset 1. We'll discuss this later, what is offset, okay. So now 42's event, 99 event will be landing to partition something, and inside that partition ordering is guaranteed. So if let's say 99 event gets first, so inside that partition P, let's say 3, 99 events get stored as offset 0. Then 42 event came, then 42 events will be stored, okay. This is the first solution. So what is the second solution? So use the event's own timestamp, okay. Instead of relying on the partitions values, who landed first or which user ID is given the first response, rely on the event's own timestamp. So every event produced by this will land on partition 0 have their event timestamp. So event.timestamp, which we can leverage in order to get rid of this confusion, okay. So the third solution is for true global order, use a single partition. Why to do this? For global orders, let's say any user ID, any of the things, use the single partition, but that again will have their own challenges. So universal ordering across every event regardless of key will not mention any key. The blunt option is a topic with only one partition. There is only one partition. Every request came, get here. No confusion. We get a perfect global order, but we gave up all parallelism. Separating it to multiple partitions, we have scalability, we have parallelism, but making it to only single, we have lost or we have gave up with parallelism. one broker, one consumer, no horizontal scaling. Okay, now let's wrap up this video by learning some of the jargons definitions and some diagrams. Okay, so what topic is a named category of message like a label or a folder, just like here orders. What is partition? One physical ordered append only log that a topics is split into for parallelism and scaling, like multiple partitions single broker can have. So partition is a physical ordered append only log that topics is split into. Why append only log? Inside the partition one event came, two event came, appended. Again another partition, one event came, two event came, so appended. So order split into order 0, order 1, order 2. I hope topic is clear, partition is clear. Now what is broker? Again the same definition I am repeating. A top broker is a single Kafka server that stores and serves one or more partitions. Inside the broker we have partition 0, we have partition 1. You can see this example. What is this? This is the topic. What is this? We have different partitions. What is this? Lands in broker 1, broker 2, broker 3. Okay. Now you have some confusion that how partitions are assigned to broker. You have seen that any message will land to partition 0, land to partition 1, land to partition 2 with the same formula, that hash of key modulo number of partition. Means message will land to any partition, we have some formula. Now any partition 0, 1, 2 will land to which broker? 1, broker 2 or broker 3. So what is the simple solution? So Kafka default assigner does something close to round robin. Okay, it deliberately avoids putting two copies of the same partition on the same broker. That would defeat the whole point of replication. Now what we'll do, let's say partition 0 is sent to broker 1. So again a copy of this partition 0 is not sent to broker 1 again. Okay, let's say the original copy of this partition 1 is sent to broker 1. Okay, now the copy of P0 is not sent to broker 1 again. Okay, it will be sent to broker 2. So partition 0 can be sent to broker 1 and broker 2. I'll show you the round robin how it follows. Partition 0 is sent to broker 1 and follower is broker 2. One is the leader, one is the follower. 1 is sent to broker 1, 2 is sent to broker 3, 3 is sent to again broker 1, 4 is sent to broker 2, 5 is sent to broker 3. The follower, the replica will go to 2, 3, 1, 2, 3, 1, 1, 2, 3, 1, 2, 3. It makes sure that the original and the replica will not land to the same broker. Okay, I hope this is clear. So let's have some other diagrams. That is topic, this is the storage, event send and appended to partition 1, producer client 1 sending this, it land to this partition, it land to this partition, it land to this partition, it land to this partition inside this topic. And you'll ask that when consumer will get the information that okay, consumer is about to fetch the information. How consumer will get that which partition I need to look at, which topic I need to look at? This is the metadata. The consumer get this metadata, topic, orders and partitions. Partition 4. The leader is broker 2. What are the where all replicas are there? So partition 2, partition 4, you can find it in broker 2 and broker 3. Among broker 2 and broker 3, which is the leader? Broker 2. In sync replicas, broker 2 and broker 3. So this is how metadata looks like. Okay. So I hope everything is clear till now, whatever I have explained. Okay. So I hope whatever I have explained is clear till now with a clear understanding of basics or introduction to Kafka. So this video is all about Meet Kafka part 1. Next video will be all about Meet Kafka part 2. Okay, so thank you for watching and having patience. So thank you so much.